Good morning, Synoptic Meteorology. This is the lecture on practical numerical weather prediction. I'm sorry that I can't be with you today, but hopefully you'll gain a lot from watching this video, as well as looking at Chapter 10 of your textbook, which has a wealth of information about numerical weather prediction specifically related to synoptic meteorology, as well as the complete comet module that is part of the online course that they have that you're going to do part of tomorrow in the Tuesday lab section. And so I often like to begin various segments of the course by looking at the history of that segment. And so I think it's always good to figure out where we've been to know how we got where we are. And so this idea of using equations to solve them for the future state of the atmosphere was actually first proposed by Cleveland Abbey of the U.S. Weather Bureau back in 1901 in a paper in Monthly Weather Review. I have posted that paper, as well as the paper done pretty much simultaneously by Wilhelm Bjerknes in 1904 to Blackboard. Now, back in the time, we think that they both independently came up with this, and really should both be credited with this concept of how we can determine the future state of the atmosphere by using our known equations. Now, of course, back in the early turn of the 20th century, we did not have the computer technology or even all of the mathematics yet to successfully complete this concept of numerical weather prediction. And it took all the way until the 19-teens when Lewis Fry Richardson first attempted this numerical forecast. Unfortunately, his attempt failed pretty epically. He was an ambulance driver in World War I. He was a pacifist, and so he used his idle time to do a calculation of the weather over Germany. And it turns out that he had an epically bombed cyclone. It ended up in 6 hours dropping by 145 millibars. And so unfortunately, due to poor initial conditions and poor smoothing of some of the data and really not having all of the knowledge that we needed yet to really successfully do this, he was not successful. He did all of this by hand, so it's amazing to think about how many calculations it would have taken for him to do that and how many years it would have taken. I have the book that he ended up writing that talks about how he did this, and so if you'd like to see that, please come and see me. Unfortunately then, we didn't have much progress over the intervening couple of decades, but then because of military use and military development, we developed the computers. We developed early computers through World War II. And so by the end of World War II, in the late 40s and then into the early 50s, we really had a rebirth of numerical weather prediction for use in meteorology. And so it is a man by the name of Jules Charny, who was at the Institute of Advanced Studies at Princeton University, that really led the charge, and with some of the folks there, including von Neumann and Fjortoff, were able to successfully model the atmosphere for the first time. Now, their initial workings did not work well in terms of timelines, right? So it took a long time to do a 24-hour forecast. I believe it was 24 hours for a 24-hour forecast. But they were the first ones to successfully produce a numerical weather prediction that actually looked like the weather and looked like it told a good tale. And so then there was quick development as computers continued to improve, and regular operational modeling began in the mid-1950s in the United States and has been ongoing ever since. And we're going to see that we've vastly improved our numerical weather prediction models through time. But really, what is a model? There are many different types of models that we can think of. In terms of meteorology, there are two primary models we have. We have physical models. And so we've just been talking about the life cycle of mid-latitude cyclones. That would be a physical model, a way to represent a physical process. But then there's this idea of dynamical models. And that's what numerical weather prediction is. We are going to use equations, and specifically our governing equations, to emulate the atmosphere and predict into the future. That's a pretty tall task. Okay? And so we've talked about the 7 equations that are needed for this endeavor. It's the 7 equations that govern all atmospheric motions, and so these are partial differential equations. Yes, they are partial differential equations, and if you are really interested in partial differential equations, you can take a class on that from the math department. But our 7 equations, just again to remind us here, are 3 Newtonian equations of motion, U, V, and W. as well as mass continuity, so our three equations of motion, mass continuity, our ideal gas law, the thermodynamic equation, and the moisture conservation equation. And so what we have are these 7 equations that form a complete set, but we can't close this set, okay? Because we have more unknowns than equations. And so when we go to model the atmosphere, we're going to have to figure out, well, how can we discretize these equations, and then how can we ultimately represent all of the different processes that are going on in the atmosphere to describe and define atmospheric flow, both in a current state and in a future state. So what we have to first do is think, okay, well, how can we represent then the atmosphere on our globe, right? Unfortunately, we live in a 3-dimensional space, but it's really hard to figure out how to go ahead and represent this whole thing. And so we have to discretize our equations, as we previously said, but then we're going to have to discretize space and time in order to successfully produce a future forecast. And so the one main way we can do this, and maybe the more easily conceptual way we can do this, is by basically cubing up the atmosphere. And so here's just an image that kind of idealizes this way of cubing up the atmosphere. And so within this cube, right, we're going to define things like temperature and moisture, pressure, U component of the wind, V component of the wind, W component of the wind, right? And within the cube, these parameters have to be homogeneous, right? The same throughout the cube, okay? And so basically we're saying an area of 20 kilometers by 20 kilometers, maybe by 500 meters in the vertical, is all the same. Now, if we think about that, do we often get areas that are 20 kilometers by 20 kilometers that truly have uniform characteristics? No. And that's going to be a limitation for us. And so the easiest way to do this is to grid up the atmosphere, cube up the atmosphere, make these grid cells, if you will, and define all of those parameters in the center part of the cube. Okay, that would be an unstaggered way of doing our prediction. This is the way early numerical weather prediction models worked. However, more recent models, and specifically the WRF model, uses grid staggering. Grid staggering is a way that we can then cube up the atmosphere basically with 2 different sets of cubes. And through those 2 different sets of cubes, we can define different parameters on different parts of those cubes to enable a better prediction. So this is the C organization, the C grid staggering that the WRF ARW uses. So I run the WRF here for us operationally twice a day, and it uses this C staggering. And so what ends up being the case is that we have our mass field, which our mass field here is contained of our temperature, moisture, and height fields, separate from our momentum fields, right? Our U and V components. So that's what's staggered here. And by doing so, we improve the ability for us to more accurately represent the atmosphere in our equations and our discretion of those equations and ultimately our future forecast. So it's a benefit to stagger. It makes some things more complicated, but again, in the end, it makes it better. So now here we just have a simple kind of 4-cell grid. But if we think about whether we're going to try to represent the global atmosphere or even just a regional atmosphere, we're going to have lots and lots and lots of cubes or grid cells. And so here's just a simple representation of basically looking over the Atlantic Ocean, that we have to represent our entire atmosphere, both in the vertical and in the horizontal, with grid boxes or grid cells or cubes. And all of these grid boxes are going to have to communicate. So that's what we see here with our arrows, is that our grid cells have to communicate with each other both in the horizontal, in the vertical, and then we may even need to go into the ocean. Well, I can't really see that blue there, so we'll go ahead and switch colors. Right? We may even have to go into the ocean because, of course, ocean processes play a role, or into the ocean, or maybe even out of the ocean, right? Warm ocean water is influencing the atmosphere. And so we have to have all of this communication on. And so if we think about how we can represent the atmosphere, we may need thousands, if not millions of grid points if we are going global with our forecasts. And that each grid cell is going to have to define temperature and moisture and geopotential height and the U component of the wind and the V component of the wind and the W component of the wind. All of our parameters we're going to need to define at each and every grid cell and use those to forecast the future state of the atmosphere. This is a massive undertaking, and so if you've taken any computer-based class where you talk about arrays, here's a classic use of 3, 4, or even 5-dimensional arrays to be able to make it more concise to then actually do all of these computations. This is also why our numerical weather prediction models are still largely based in Fortran and C compiled languages, because those compiled languages are fast, and fast to do these millions of computations that we're going to have to do every couple of seconds to complete a 72-hour forecast or a 384-hour forecast in the case of the GFS. So we've got all of these processes going on. We've got all of these grid cells where we have to account for all of the information to describe the atmosphere completely. But what can we actually forecast? What can we actually predict with any sort of accuracy? And so this goes back to our understanding of grid spacing. Grid spacing here is basically defined as the distance in meters between the center parts of our cubes or the center parts of our squares in this image, or the center parts in our vertical grid spacing here. And so we might run a grid with a grid spacing of 13 kilometers in terms of the current NAM construction. Or if we're running a higher resolution version, we might run it at 4 kilometers or 3 kilometers. Or if we're really lucky and have good computational speed, 1 kilometer. But that doesn't mean we can actually observe things that are 13, 4, 3, or 1 kilometer big. Okay? Because grid spacing does not equal resolution. Basically what we're doing here, we have all of these grid points at which then we need to define the atmospheric characteristics. And so if we think about the atmosphere in terms of our trough ridge system, right, we're going to need a couple of grid boxes in order to define this wave. And so we know we have a grid point here, and we have a grid point here, and here, and here, and here. And so as we go along, it turns out that we need at least 8 grid cells, 8 grid points, to fully define a wave, to say that we would resolve that feature. And so really, we're limited by 8 times the grid spacing for what we can actually resolve. And so if we think about a wave, if we have a 20-kilometer grid spacing, that means the minimum feature that we can represent are features that are bigger than 8 times 20 kilometers, which would be 160 kilometers. There are many small-scale features, even wave features, that are much less than 160 kilometers. Even if we had a 4-kilometer grid spacing, 4-kilometer grid spacing times 8 grid points would be 32 kilometers. And so we're only going to be able to resolve features that are 32 kilometers or bigger. And of course, more grid points to define a feature, theoretically the better the prediction should be. But even if we just take a single grid spacing, so not even what we're resolving, but if we have a 4-kilometer grid, we're going to need to think about, are there processes that are smaller than that we need to account for that actually don't occur on the grid spacing? And so we're going to come back to that in just a little bit. But our problem is not only in the horizontal, as we see in this image here, but that we also have to discretize our space in the vertical. And the vertical becomes a problem because in order to well discretize our equations, we need to have all of our grid points defined everywhere. And we can't have them just go into the ground. And so we need to have something that can be what we call terrain following, so that each grid point on every quasi-horizontal level can be defined, and we can then do this discretization. Hard word to say. And so one of the most common vertical coordinates that is terrain following is the sigma p coordinate system. And so we've got the definitions up here. They're just up here for your purposes. Not going to be tested on can you calculate a sigma level. But again, it's important to define this grid following coordinate system. And so you can see the sigma levels here over on the side. And we can see when they're right at the ground, it follows the ground at sigma equals 1. And then as we go up through the atmosphere, sigma goes from 1 to 0. And at 0, we have a constant pressure surface, which is at the point we've declared that is the top of the atmosphere, often 5 or 10 millibars, which would be well above the troposphere. And so we can see as we go up, our surfaces become less sloped as the terrain is less of an impact on those surfaces and might eventually be just the same as a constant pressure surface. But the key here is that our coordinate system is terrain following, so that this surface is always defined and we always have grid points, even when we're going over the terrain. Another version here is the eta coordinate system. There actually used to be a numerical model called the eta. And the eta, instead of being this smooth terrain following, would represent things by different levels, right? And it would be called often a stepped terrain. And so it would take the average and then create a box so that we can have a nice stepped terrain. This had benefits to it, like cold air damming was better represented in this kind of terrain rather than these smooth sloping surfaces, because it causes problems with some of our calculations of pressure gradients and stuff like that with our smooth terrain. But again, the most common one now is sigma coordinate systems that is used by things like the WRF. Alright, so we have all of these grids in the horizontal, in the vertical, but then how do we actually get data onto these grids? Right? This is a big process. And this is actually where a lot of work is being done and where a lot of work needs to be done in the future, and that's data assimilation. Data assimilation is the process by which we take our observations, combine it with a short-range forecast or a first guess field, to then ultimately come up with our final analysis. Now, the problem is that our first guess field is a short-range forecast, which may or may not be accurate, which we have to combine with our observations, which again may or may not be accurate, but are our best representation of what is known about the atmosphere. And so we have to combine these two things to create a better analysis. And so what we have to do is we have to increment our short-range forecast, our first guess field, by the observations, but we have to also quality control. As we see this one observation here that is present in our observations doesn't seem to really conform with the data, and so it might be bad, and so we may have to take that out. And so then we're going to take this observation increment, correct it to our obs, make a better increment here to then change the analysis to bring the analysis more in line with our observations, and that we may have to do this a couple of times. We have to cycle this. Okay? We have to cycle this because we want to minimize the errors in this analysis field. By minimizing the error in the analysis field, we know we have the best possible representation of the atmosphere. That does not mean that it's perfect, but it's the best representation we can come up with to then start our forecast model, which then produces our output that we use as synopticians and as forecasters, and that then forecasts from this model serve as the next first guess field back into our data assimilation scheme. And so there are currently two primary ways about which this data assimilation happens. There's the 3D var schemes, 3D variational schemes, and 4D variational schemes. The 3D variational schemes are what are currently used by US operational weather models. And those schemes, specifically for the GFS, basically set up a time increment through which observations can come in, and they're basically all put at the same time, say 0Z for the 0Z forecast. And then it'll do this process of incrementing the observations to get the best possible observations for 0Z to start our initial value problem with. Better schemes, though, use four-dimensional variation. Four-dimensional variation keeps that time element to more appropriately put observations with the time that they occurred, so that the observations aren't just lumped together at 0Z despite the fact that they may have been taken an hour before or an hour after 0Z. The European model, the ECMWF, uses that four-dimensional variation scheme. NCEP is currently working on implementing four-dimensional variation schemes for the GFS, which is being done in hopes of improving the forecast of those schemes, because it is a much better way of getting observations onto our grid in the most accurate way possible. Now you can take a whole class or even classes in data assimilation. It involves a lot of linear algebra, and I don't even know that much about it, but this is the overall process that's going on. And so we have to take the raw observations, previous forecasts, to then increment and cycle through and minimize our errors to produce the best analysis to start our initial value problem with the best analysis. Alright, so we've gridded up our atmosphere, we've gotten data onto our grid. Now how do we actually do this prospect of numerical weather prediction? We are ultimately trying to predict the future. If you think of all the different ways that various disciplines try to predict the future, most fail epically. Meteorology, however, does not, and we'll show that at the end, near the end of this lecture. It turns out that meteorology is lucky. Meteorology and the flow in our atmosphere are governed by physical laws. And so we utilize those physical laws in order to predict the future state of our atmosphere. And we were actually given props by Nate Silver, 538 founder and author of The Signal and the Noise, an excellent book about prediction, about how meteorologists do it well and think about the process well, unlike other disciplines that unfortunately have to rely on trying to forecast and predict human behavior, which is not always following perfect laws because humans aren't perfectly rational, which is probably a good thing because we'd be really weird if we were. But how do we do this? How do we predict the future? There are two primary ways we do this: finite difference and spectral. So a large way that we can conceive of this idea of numerical weather prediction is by using simple advection schemes. Advection is a large driver of how air flows around the atmosphere and how parameters like temperature move around the atmosphere. And so we can represent this with centered finite differencing, which is developed from Taylor series expansion. So to bring back all that wonderful Calc 2 material and stuff from dynamics. But here, instead of just using central differencing to figure out, say, like vorticity, we can solve for the future state of the atmosphere. And so we can solve for the final temperature based on an initial temperature at our grid point and looking at our grid points that surround us, I+1 and I-1. We'll see an example here on the next, in the next few slides. But then we have this little parameter here that we have to concern ourselves with. Okay, our advector u, so that's basically the wind speed. How fast are we advecting it through? We multiply by our time step of our model, and we divide by 2 times the grid spacing, right? That just comes out of our Taylor series expansion, the 2 times the grid spacing. This is a limiting factor, and we're going to talk about that limiting factor in just a few slides. Okay, but we're going to have to do this calculation at every single grid point. So we're going to have to do millions of calculations in order to get even a 24-hour forecast. Now imagine being Louis Fry Richardson in the 19-teens doing this all by hand. It's not surprising that it wasn't successful. And it's not surprising that it was only successful once we actually got computers to be able to do the bulk of this work for us. So just a little bit more on grid points and finite difference models versus spectral models. Grid point models are often regional. They're over what we call a limited area domain. Not only is it an initial value problem, but it's also a boundary condition problem. We must feed in observations or weather systems that are coming in from outside the boundary in order to get a successful prediction if we go beyond about 6 hours of forecast, which of course we would want to do. And so we get errors due to truncation in the finite differences, errors due to the finite difference in space and time, as well as the discretion of our equations in and of themselves. Spectral models are just a different way of doing this, as we previously mentioned. This is often used for global models. So for example, currently the GFS and the ECMWF are spectral models. Often these global models are what are providing our lateral boundary conditions for our grid point models or any limited area model. These are only initial value problems because with spectral models, our boundary condition is periodic, meaning the end equals the beginning, right? If we think about a wave, going across the globe, right? The end meets up with the beginning at some point, and so we have a complete system there. In general, they're considered numerically more accurate because we don't have any finite differencing in space. We'll still have to have finite differencing in time, which introduces errors. But again, for more information, go ahead and look at those comment modules or take a class in numerical weather prediction. But let's investigate a little bit more this idea of grid point models and this finite differencing advection schemes. And so here's a simple example. If we are ultimately looking at making a forecast for St. Louis, right, we're going to know that, oh, hey, our wind is advecting by 7 meters per second from west to east. Our distance here, delta x, is 100 kilometers. And so two important grid points here for us are going to be this grid point, which is to the west, and this grid point, which is to the east of our point that we are trying to forecast, which is right here at St. Louis. And so our centered finite differencing is going to use the two on either side to predict then the blue box using our 7 meters per second and our grid spacing there for our prediction. So we see I minus 1 and I plus 1 for our different places, going back to our equations. And so initially our equation is set up as dt dt, so the change in temperature with the change in time equals minus u, our advection, times the change in temperature over the change in space, which we can discretize and solve for the final temperature, which gives us the equation we had before, to ultimately get our final prediction for St. Louis. And again, I have simple things that illustrate this idea of finite differencing, and if you are interested in learning more about it, please feel free to come and see me. But this whole prediction is predicated on the fact that we can't have air move through an entire grid spacing in one time step. Okay? And that number that was out in front of our prediction equation that we saw a couple slides ago was this u times delta t divided by 2 delta x. That parameter is called the Courant number. And the Courant number is a limiting factor for us in numerical weather prediction. It limits the time step that we can choose based on the speed of the wind within our domain, and really the maximum speed of our wind within anywhere of our domain, and the grid spacing. And so there is a condition for computational stability that is listed here. Delta t less than or equal to delta x divided by c. Okay? And so that means our time step gets chosen based on our choice of grid spacing, say 4 kilometers, divided by the maximum wind speed within our models. And so, for example, in synoptic meteorology and for most numerical weather prediction systems, right, we have to consider what would the jet speed be. And so if we have a jet speed of 150 meters per second, and we have a grid spacing of 4 kilometers, that is going to greatly limit the time step we can choose. And so that's often why our time steps are between 60 and 90 meters per second. Or excuse me, 60 and 90 seconds, meaning that basically every minute we're going to have to do the calculations for every single grid point across the entirety of the domain, both in the horizontal and the vertical. And so by lowering our grid spacing, by lowering this delta x, we greatly increase by 2 to the 4th our computational expense. It just takes that much more computations because we're going to have to lower the time step. And so that's why lowering grid spacing is great, but it also takes really, really fancy and fast computers to do this. If we violate this condition, if we violate this CFL criterion, it turns out that bad things can happen in the model. So here's an example from December of 2006 in the NAM, where all of a sudden there are these spurious waves, and they are right around where our large jet stream is. Jet stream in excess of 150 knots. Looking at another level here, this is our surface level. Whoa, what's going on there? Well, it turns out, and you can look at the comments here from NCEP in a publication that they put out related to this. Important note, numerical instability associated with very high wind speeds, greater than 120 meters per second, forced by anomalous stratospheric events, caused these numerical instabilities. These waves were not real, but yet they occurred in our simulation because of too big of a time step. Parcels of air were moving through our grid cells before a time step could occur. So what did they have to do? They had to reduce the time step, which made all the products run a little slower, and so then you can see a reduction will temporarily cause a 4-minute delay in the delivery of GFS products. 4 minutes, not that bad, but still a non-zero amount of time for when we are really running on waiting for some of those solutions to come about. So don't violate your CFL criteria, otherwise your model go whoop kablooey, which it did for the GFS back in December of 2006. Alright, so we've seen a little bit about how this whole numerical weather prediction enterprise happens, but then what we really need to do is we need to really talk about the limitations that come from numerical weather prediction models. And so there are 3 primary areas through which we can get errors. We have errors in initial conditions, errors from the model itself, and intrinsic predictability limitations. Some of these we've touched on a little bit, and so we'll rehash them, but we're going to talk about each of these individually here in the next few slides. Errors in our initial state. There are so many ways in which small amounts of error can get into our initial state of our atmosphere, which is ultimately what we're starting our forecast with. If you've taken instrumentation or know anything about instrumentation, we know that our instruments can't perfectly represent the atmosphere, and there are only estimates of temperature, really, in the end. And so those errors are inherent then in our initial conditions. We don't have observations that are across the entire globe enough to fill a 4-kilometer grid, so we have representativeness errors. Right? Do we represent every valley or every ridge accurately with our temperatures with instruments? Of course not. And so we have representative errors. And then, of course, instrumentation can fail. Data transmission can fail. And so we have quality control issues that we need to account for that can also introduce errors into our initial state. Even if our data was perfect, we then have to grid up these observations at discrete points. That inherently smooths some of our data, and this data assimilation process can introduce errors as well. And so in the end, we have too few observations for our analysis, both spatial density and temporal density, which are real limitations to our initial state predictions. Couple that with errors in our model. Our equations of motion are incomplete. They are not a closed set of equations. By discretizing our atmosphere, both in space and time, we introduce errors in our numerical approximations. Our horizontal and vertical boundary conditions are not perfect, right? We use forecasts for horizontal and vertical boundary conditions that may not be accurate in and of themselves. We don't perfectly represent terrain either, right? Even with 4-kilometer grid spacings, we represent terrain a lot better than we used to, but still not accurately. And of course, terrain can greatly influence many of our important weather phenomena. And so this idea of inadequate resolution comes to bear here, right? We keep getting smaller and smaller grid spacings, but we can't always resolve things. And so how do we still represent things we can't resolve? And in actuality, we have to think not even with what can we resolve, 8 times the grid spacing, but even our 4-kilometer domains. Can you think of things that are occurring less than 4 kilometers? That the size of that event, that size of that process is smaller than 4 kilometers? Of course there are. There are lots of things that are occurring within the atmosphere that we really must account for that are much smaller than even 4 kilometers, than even 1 kilometer. All of these things we must still account for and parameterize, meaning we must come up with some equation to represent the process. So for example, boundary layer processes. For example, radiation and the scattering, right? Why is the sky blue? The sky is blue because of scattering of light. Well, what size are the particles that are doing the scattering? They're microns, nanometers in size. We're never going to get to a position within atmospheric science where we can represent all of those processes on the grid scale, because then we would need to know the position of every single molecule in the atmosphere, which is never going to happen. Even convection. Cells are typically 20 kilometers big or bigger. And so only on 4 kilometers or less are we really starting to resolve even just elements of that convection and not even everything in there. And so we're going to have to parameterize all of these sub-grid processes. And so here's just kind of a summary slide of the different processes that we must take into account. We're going to talk about some of these individually here in the next few slides. But incoming solar radiation we need to account for. Clouds, snow, rain, surface roughness, latent heat release, sensible heat release, all of these different processes, turbulent motions, we must account for them all. And depending on our grid scale, we're going to have to parameterize different things at different times. And so here's kind of a summary slide that gives where we have and absolutely need convective parameterization on scales that are larger than 12 kilometers, versus where when we get to 4 kilometers, we can allow convection to happen explicitly within our model and no convective parameterization is needed. But even then, our parameterization schemes might change depending on scale. And so we're going to have a planetary boundary layer parameterization that might work well for small grid spacings to large grid spacings, but if we get really small, then we're going to need large eddy simulation schemes to most accurately represent those parameterizations. And so this is a whole subfield and where great improvement can come in our model, because a lot of our parameterization schemes were built for models with grid spacings of 20, 40, 60, 100 kilometer grid spacings. Now we're using some of these very same parameterization schemes on 4 kilometer grid scales. And the accuracy may not be great. And so let's look at an example of convection to talk about what is subgrid scale. And so here is a grid spacing of 60 kilometers. And so if we have scattered showers and thunderstorms, we might have many different cells that are contained within a 60 kilometer grid, right? Because our cells may only be 2, 3, 4 kilometers wide. And so how do we represent this convection within our model, right? These storms are sub-grid scale. Our grid box is not even saturated. So how does our convective parameterization scheme work with, say, our microphysical scheme to be able to do this convection, to be able to produce that convection, because obviously it's still going to impact our forecast. Even organized convection is still smaller, is still sub-grid scale when we're talking about our 60 kilometer grid spacing. And so we have to parameterize that convection. Moving now to 12 kilometers, here we're starting to get into a murky area, right? Some elements of our organized convection seem to be represented by grid cells, but some of them are not, right? Some grid cells are saturated, some are not. Really here our storm is being partially resolved. And so how do we handle that? Right? Both our microphysics and convective parameterization schemes are going to have to deal with this. But as we continue to reduce our grid spacings, say here to 3 kilometers, right, now we can fully resolve and well represent this idea of convection. And so a convection scheme is not required, but we're going to have an appropriate microphysical scheme in order to handle the creation of clouds and hail and precipitation falling out of this convection. And so these are not simple things to do. And so here's an example of a squall line moving through. There are certain elements of this real MCS that will be well resolved by 25 kilometer grid spacing, as is indicated in this figure. But of course, all the details of that minor convective structure, basically where we see the most intense cells, are definitely going to be smaller and smaller than our grid, and thus not well resolved. So convection is something we're going to have to parameterize in ways, and how do you do that? It's not an easy process. There are multiple different ways to do that. Some do it better than others for different types of phenomena, which of course can occur at the same time, which makes it even that much more difficult. Another example is radiation here, right? Radiation is occurring on scales that are very, very small. And so how do we get that shortwave solar radiation coming into the atmosphere, heating the ground, which then by heating the ground, we're going to re-radiate that to the atmosphere and warm it and create thermals, which creates turbulence. But what if there are clouds there? That's going to reflect a certain amount of the radiation, which then is not going to make it all get to the ground, which is going to reduce then some of our latent heat release to the atmosphere, but then the clouds are going to be radiating in and of themselves. And all of this is occurring on grid scales that are much smaller than even 1 kilometer. And we've got to be able to represent this. And so if we just think about clouds for a second, how do we even do that? Right? We have to basically think of what fraction of the grid cell is being covered by clouds. Is it 10%? Is it 70%? Is in this example? Is that over a 30-kilometer domain? Is it over a 10-kilometer domain? What does that mean? That's going to augment how much solar radiation is getting in, or escaping, or re-radiating. All these different factors are impacting, which of course then when we're talking about clouds, we're talking about moisture. When we're talking about clouds, we may be talking about convection. All of these things are interacting. Even our land surface schemes are greatly important, right? This is where our solar radiation is coming in and then being re-radiated to the atmosphere, melting snow, evaporating water. We're having heat fluxes both into the ground and into the atmosphere. All of these processes are having to be accounted for. And we have to come up with equations to represent these processes, even though we can't represent it on the grid scale. Here for water, remember, water is weird in the atmosphere. The most sophisticated schemes have water vapor, have cloud water, have cloud ice, have rain particles, have snow particles, have graupel. All of these different particles are constantly interacting with each other, and so you see all of these different arrows. Each arrow in this case indicates different processes. And so for example, we have condensation and evaporation, so we can go from vapor to cloud water, but we can also go from cloud water to vapor. Each arrow means that we have to have at least one equation to represent that process. At least one. Look at all the arrows here, right? There's lots of things going on, right? Then we can auto-convert cloud water to rain. We can accrete cloud water to rain by collision coalescence, for example. But then we got sublimation and deposition here, going from vapor to cloud ice or cloud ice to vapor. We can have melting going on. We can have freezing going on. Right? All of these processes are going on, and all this interaction is releasing latent heat or absorbing latent heat. And so all of this must be accounted for. And then think about all the interactions of these parameterizations as we've been talking about them. Right? Our convective schemes, our cumulus schemes, are interacting with our microphysical schemes to produce convective rain, which is then falling to the surface, which is then causing changes in surface moisture, possibly surface temperature, which is impacting surface fluxes, which are impacting the planetary boundary layer, which is changing temperatures at the surface, which then affect things like surface emission, albedo, and radiation to space, but then radiation is coming in and warming the surface. Oh my God, look at all of these interactions. And all of this is occurring sub-grid scale. And so we have to account for it. Not an easy task. Lots of work can be done to improve our parameterizations, and recent work has been done. They're making parameterization schemes what is called scale aware. Scale aware means it knows what the grid spacing is and augments how it does its parameterizations depending on the grid spacing. Not only do we have our errors in initial conditions, we have our errors in our models, which include errors in our inability to represent all of these processes accurately. But to put on top of that, the cherry on the top here, is we just have some intrinsic limitations to our predictability. This whole process is an initial value problem. And the atmosphere is chaotic. Now, chaotic here does not mean random. What it does mean is that minor perturbations, minor errors can amplify and produce large errors in the end. Ed Lorenz is the man who kind of initially identified this as a thing in the meteorological discipline. And his theory ultimately came up with this 2-week predictability limit for deterministic prediction. And deterministic prediction here means our common weather prediction. So this is not related to climate modeling. That's a completely separate thing, and we could have a completely different lecture on that material. But it's only about 2 weeks. So when we see these 45-day predictions from things like AccuWeather, they cannot use deterministic prediction to successfully complete that. They have to use other forms of climate prediction for that, or seasonal prediction that may use more statistical predictions rather than this deterministic finite difference method that we've been describing here. But this is also a benefit, because from this chaotic nature, from making small little changes to our initial conditions, we can run models multiple times to produce a wide range of answers, or an ensemble of solutions. And from this ensemble, we're able to then gain a better idea of how predictable the atmosphere might be. If all members of the ensemble are saying roughly the same thing, that will allow us great confidence in predicting the atmosphere, right? Minor changes did not cause major changes in the solution. And so a way to represent this idea of ensemble that Ed Lorenz did when he initially did some of his work, he found that when he saved only 3 digits worth of data, 3 digits after the decimal point that is, and he reused that output as his input, he got a different solution. And so essentially to 3 decimal points, he had the exact same beginning, right? And we can see here throughout the beginning part of this forecast, as represented by this figure in the upper right-hand corner, they hardly look different. But through time, that difference in the millionth place, caused minor errors to start occurring within the forecast, such that we start to see that the forecasts diverge in the second half of the solution, and by the end are at wildly different solutions. And so initially here we would say that, oh, this system is highly predictable. And then in the end, these predictions become less and less predictable. And so when we start seeing these changes occur, which we see right here, our solutions start to diverge, that's basically where our solution reaches something called a bifurcation point, as illustrated here in the lower right-hand corner. And these bifurcation points that can kind of cause it to go off to 2 different solutions, which those 2 solutions can go to 2 different solutions, so now we have 4 different solutions, and so on. And so this idea of all of a sudden our solution breaking down to 2 different locations and then possibly going back and forth between these different solutions, we get this typical, or this emblematic butterfly model that Ed Lorenz came up with, that basically our solution can go back and forth between these 2 attractor points, never really reaching any one given solution, such that our atmosphere is not fully predictable. We can't always make a finite determination. To learn more about chaos theory and this idea of predictability limits, you can read Ed Lorenz's very accessible book called The Essence of Chaos. I also have a copy of that in my office if you are interested in it. So after thinking about all of these errors, it's pretty amazing that this whole thing of numerical weather prediction even works at all. And it turns out that we've actually been doing a pretty good job at improving our predictions. And so here we're looking at the anomaly correlation for the ECMWF of 500 millibar heights for 3-day forecasts, 5-day forecasts, 7-day forecasts, and 10-day forecasts. And so you can see here as the correlation approaches 100% or 1.0, we are greatly improving. That means the anomaly of basically the forecast error is 0. And 3-day forecasts are getting really, really good. We are approaching 98% accuracy essentially. And imagine that. Look back at 1981, right? We were simply at a little over 80, probably 83, 84% for the Northern Hemisphere. The Southern Hemisphere has taken a little longer, but it's made great strides in the recent few decades. But since the 1980s, we've greatly improved our forecasts across all forecasts. Our 5-day forecasts with the numerical weather prediction models are now as accurate as our 3-day forecasts were back in 1981. That's huge. And our 7-day forecasts are approaching Southern Hemispheric 3-day forecast accuracy back from 1981. And our 10-day forecasts were basically coming from irrelevance to some modicum of ability to predict the atmosphere. So it's amazing to see how this has come about, how our prediction has improved through time. But in the end, we are ultimately using NWP here as a tool, right? Do not use numerical weather prediction as a forecasting crutch. Don't believe what the model says just because the model says it. That is not an accurate way to go about forecasting the model. And if you write AFDs that says, oh, the model said it would, no, fail, wrong. Models will be wrong. You need to be skeptical. A single run is a single deterministic run, which may not be the best representation of the future state of the atmosphere. What you want to use NWP for is you want to use your QG dynamical understanding that you've been practicing with observations so far this semester. Utilize that to understand where and when those forcings might be in certain locations. Right? The numerical weather prediction tool can be used to help you identify location and timing of events. But that really the forcing here is still our QG forcing that we should be thinking about. And so I encourage you to make limited use of model output statistics, come up with your forecast first, and then use MOS as a way to then refine your forecast in the end to get down to actual numbers for particular locations, especially in terms of temperature and precipitation and wind speed. Ultimately, it's best to use ensemble forecasts to better round out your prediction tool set. And again, you can do the extra exercise in the comment module handout in lab tomorrow for that. But how do you keep up to date? Because obviously numerical weather prediction models are always improving. And so you can use the following link to go ahead and find the model encyclopedia that is available from essentially a comment module. This is from UCAR. And it'll have all the current layouts of what the grid spacing is, what the resolution is, what kind of parameterization schemes they're using, what the accuracy is of their finite differencing schemes, both in time and space. And so I encourage you to visit that website. And so that ends here our discussion of numerical weather prediction.